All right, welcome to Farm 251. And in this video, we'll be looking at hydrogen ion concentration. It is good to take note that hydrogen ion concentration can be applied in pharmaceutical drug analysis. Let's classify pharmaceutical drug analysis into physical, chemical, and biological, because there are different methods of doing drug analysis. These methods can be classified into physical, chemical, and then biological method. But our main focus will be on the physical classification. So under the physical classification, we can have potentiometry and then other methods such as photospectrometry. And under this photospectrometry, we can look at something that we call polarimetry. So this is basically spectrophotometry. This will be done in the lab and then you have a better understanding. Then we can also have what we call chromatography. I think most of us are conversant with this chromatography. Good. Now, similarly, under the titration, there are different types of titration that we can have. We can have the acid-base titration. We can have a titration that employs the idea of electromotive force. That's the movement of ions in the solution. That's simply the use of chemical cells in the titration. And we can also have a titration that employs the idea of electrolytic conduction. So simply in this type of titration, we'll be applying the ionic theory in the titration. When we talk about hydrogen ion concentration, our idea should, or what should come into our head should be simply pH. So the hydrogen ion concentration is what we simply call the pH. pH. That's hydrogen ion concentration. So in this video, we basically be looking at pH. But then we have to take note of certain definitions that we need to be abreast with. For example, we have definition of acid and bases by different scientists and then by different theories. So the first one we look at is free ionic definition of acid and bases. And this one, we are defining an acid to be a compound containing hydrogen, which could be wholly or partially displaced by metals. So any compound that contains hydrogen, and if this hydrogen occurs to be wholly displaced or partially displaced by a metal, then that compound qualifies to be an acid. So let's take a look at an example. We have HCl here, and then we have a metal. We can realize that this metal was able to displace the hydrogen. And then we formed a compound NaCl, which is a salt. So the hydrogen has been fully displaced from the HCl to be taken place by the sodium here. And so we form a salt and the hydrogen has been moved away completely. That means this compound HCl qualifies to be an acid based on the pre-ionic definition. Let's take another example. Let's look at a reaction between carbonic acid and a sodium metal. And what is going to happen is that because there's only one mole of the sodium metal here, we can't displace all the hydrogens in here. So we are going to have a compound like this. We're going to have sodium bicarbonate. And then you have your hydrogen somewhere. So that tells you that this is an example of partial displacement of the hydrogen. And so this compound also qualifies to be an acid. Let's look at a base. We are saying a base is a compound which reacts with an acid to form salt and water. So again, we can see a base here, which we are all conversant with, sodium hydroxide. And we can also have an acid here, acetic acid. This is a weak acid. we can see that these two compounds, the sodium here was able to replace this to give us a salt, which is the sodium acetate salt. So once you're able to form a salt from the reaction between this base and this acid, then this compound here qualifies to be a base according to the pre-ionic definition. As simple as that. The simplest example we know is NaOH and then HCl. That is going to give us our popular salt, NaCl, plus our water. It means this compound here qualifies to be a base based on the pre-ionic definition. There were two scientists, Oswald and then Arrhenius, and then they also came out with a definition that an acid is a compound that dissociates in water to produce hydrogen ions. When we talk of hydrogen ions, we can also call it the hydrozonium ion. Hydrozonium ion, which is simply the H3O+. So whenever you see hydrozonium ion, it's H3O+, and it basically uses interchangeably with H+, as you can see here. So any compound that is able to break down in solution to give you H+ or hydrozonium ions, and that compound qualifies to be an acid. Let's look at the example down here. We have HCl again, and this HCl is able to break down. So it's an aqueous solution, and it's able to break down into H+, and then our Cl-. So once it was able to break down to give us H+, then HCl, according to Oswald and then the Arrhenius, qualifies to be an acid. Similarly, looking at acetic acid here, it's a weak acid, and so we have the reversible arrow here, which is telling us that it is a weak acid. It was also able to break down to the acetate anion and then the hydrogen ion as the H+. And so this compound automatically qualifies to be an acid, according to Arrhenius and then Oswald. Let's look at a base, according to the same scientists. They are saying a base is any substance or a compound which also breaks down in solution, but this time around will produce the hydroxyl anion. This is the hydroxyl anion. So once the compound is able to produce the hydroxyl anion, then it qualifies to be a base. So sodium hydroxide here was able to break down to form sodium ion, and then the hydroxyl ion. That means sodium here, according to Arrhenius and Oswald, qualifies to be a base. Similarly, ammonium hydroxide here also does same, breaking down to this, and then the hydroxyl ion. So this qualifies to also be a base according to Oswald and then Arrhenius. Let's look at the definition from Lowry and then Bronsted. I think we are convergent with the definition from SHS, Bronsted-Lowry definition of acid and base. But they are saying an acid is simply a proton donor, then a base is a proton acceptor. Let's digest this and understand it better. When talking about a proton, we all know a proton has a mass of 1. Is that okay? So when you look at hydrogen, a typical example of a proton is hydrogen, because hydrogen has a mass of 1 and then the atomic number of also 1. So this qualifies to be a proton. So in chemistry, we are mentioning proton, donation of proton is basically talking about donation of hydrogen. Okay. And in pH calculation, when you say a proton, you're talking about hydrogen. Okay. So once the compound is able to donate hydrogen to another compound, then it qualifies to be an acid. Similarly, if this compound is able to accept this proton from another compound, then it's a base. So let's take a look at an example here. We have HCl and then water. In this case, let's see which one is going to be our acid and the base. Let's look at the products from here. We have the hydrozonium ion here, and we have the Cl-. We can see that this HCl here was able to give this hydrogen to the water to give us the hydrozonium ion there. It means that this HCl was able to donate the proton and so therefore qualifies to be our acid, as we can see here, qualifies to be our acid. Again, once this water was able to accept the high proton from the HCl, it qualifies to be our base, as we can see here, qualifies to be our base. Then an example again we have here is the HCl, and then as our HCl and ammonia. And so our HCl was able to donate to the ammonia to give us this ion here, and then the Cl minus. So that is basically what we are talking about. Okay. So moving on, we should take note that hydrogen ion concentration is simply a measure of the acidity of a compound and is expressed by what we call the pH scale, which most of us are conversant with. Also take note that when we mention something like a fully ionized solution, we are talking about a solution of a strong acid or a strong base. So a solution of strong acid or a strong base is what we call is a fully ionized solution. Why? Because a strong acid and a strong base is able to break down completely in solution or ionize completely in solution, and so qualifies to be called a fully ionized solution. And when they have a fully ionized solution, let's say of a strong acid, the pH is simply calculated by the negative log to the base 10 of the hydrogen ion concentrations in that solution. For a fully ionized solution of a strong base, we can simply have the POH to be given as the negative log to the base 10 of the OH minus concentration in that solution. So this is for a strong acid solution, this is for a weak acid solution. Similarly, for a partially ionized solution, it means that that is simply a solution of a weak acid or a weak base. So for partially ionized solution, you're looking at weak acids and weak bases. And for those ones, we are saying that the H plus concentration in them is basically, for a weak acid solution, the H plus concentration is basically the square root of the acid dissociation constant multiplied by the concentration of the solution. It means that we can simply have the same thing for a weak base. So our OH minus concentration, OH minus concentration will be equal to the root of, this time around, not Ka, but Kb times C. Kb because it is a base, and so we should have a dissociation constant for the base, no more the acid. So this is for a weak base, and this is for a weak acid. Now let's base on this to derive, to understand this here. To understand this one. Okay. So we are saying that when you have a solution of a weak acid, okay, solution of a weak acid, the H plus concentration is basically equal to the root of the acid dissociation constant multiplied by the concentration of the solution. But then our interest is to get what we call the pH. We said, we look at it earlier, that pH is equal to negative logarithm to the base 10 of the H plus concentration in the solution. And so therefore, I can take negative log of this side. And once I take negative log of the left-hand side, I do same for the right-hand side. So I'll take a negative log of this side too. I'm going to get this. Good. But once we are saying pH is equal to negative log to the base 10 of H plus concentration, that means I can replace the whole of this thing here by pH. And by basic logarithm or by basic idea that we have from SHS, we know that when we have anything like, let's say the square root of a is the same as a to the power half. So I can translate the whole of this thing and write it as negative log of KAC all raised to the power half. Does that make sense? Good. So once again, from basic logarithm principle, when we have something like ax raised to the power n, the log of ax raised to the power n, this can easily be translated as n multiplied by the log of ax. So let's translate the same idea here. So we have pH being equal to, this half here will come down here to multiply the whole thing. So we have negative half log KAC. This is what we are going to have. Good. Now, once we have this, once again, by logarithm, we know that whenever you have a log of, let's say, log of AB, this can easily be translated into log of A plus the log of B. And so we can also move the same idea here by saying pH is equal to, then I'll just open up this by saying negative half log of Ka, and then ideally it's supposed to be plus, but the negative sign here will take over. So minus the same half multiplying the log of C. So that is what I'll have. But we know that whenever you see negative log of Ka, it is basically what we call the pKa. So I can say that my pH is now, the whole of this is the same as half multiplied by negative log of Ka. I can say my pH is half pKa, and then I have my minus half log of C. So that is what we saw in the previous slide. This is what we saw in the previous slide. So you can see it here that we have our pH being equal to half pKa minus half log C. Okay. You can try a similar example for the beads, and let's see. So this time around, you not have H plus being equal to root of KAC, but you have this OH minus being equal to KBC. Try it and let's see. Try your hands on that at your free time and let's see how it goes. All right. Let's move on. Moving on, by analogy, we can say, I mentioned earlier that when you have a fully ionized solution of a base, then the POH is simply the negative log of the OH minus concentrations. That's very fine. Good. Once again, like I said, I asked you to prove this earlier. So try doing it. So this for weak bases. For weak bases, the POH will be equal to half pKb minus half log C. So try your hands on that at your free time. For a neutral solution, we should know that the H plus concentration is always equal to the OH minus concentration. And so therefore our pH will be 7. This is basically what we know that for a neutral solution, the pH is 7. Good. But for an acidic solution, our H plus concentration will be more than 10 power negative 7. When we take negative log of this, you are going to get 7. So it simply means that for a strong acid solution or for an acidic solution, the pH must be less than 7. So pH ranging from 1 to 6 qualifies to be in the acidic region. But for a base, the pH must be more than 7. From 7 point whatever, ranging to 14 qualifies to be a base. So this is the pH scale, and then we can see from here that it ranges from 7 to 14. So anything in this range is in the acidic region, acid, and then anything in this range is in the basic region. Very good. This is a popular equation you should take note of. that pH is always equal to 14 minus pOH, or in other words, 14 is equal to pH plus pOH, any other way you take it, or pOH, just by a change of subjects, be equal to 14 minus pH. So this is basically something you should have at the back of your mind. Let's look at the last type of definition by a scientist called Lewis. Lewis defined an acid to be a molecule or ion that accepts an electron pair to form a covalent bond. So for Lewis, it doesn't matter if the thing is even an ion. There's an ion and it's able to accept an electron pair to form covalent bond, then it qualifies to be an acid. Now, whenever there's a covalent bond and there's donation of electron pair by just one species, we call that as the dative bond or dative covalent bond. So simply, whenever there's a formation of dative covalent bond, then we are likely to have an acid in the base inside the system there. And the base is the other way around. We are saying a base is a substance that provides a pair of unshared electrons by which the base coordinates with the acid, or simply that species that will donate the pair of electrons is the base. An example, let's look at the species here, boron trichloride was able to bond with dimethyl ether. But we can say that dimethyl ether has a lone pair here. That is, was able to donate to the boron trichloride to form the compound we are having here. It means that this dimethyl ether, once it's able to donate the electron pair, by the definition we saw earlier, it qualifies to be, we are saying that an acid is that one that accepts the electron pair. So it means that this boron trichloride here qualifies to be the acid. And this one donating the electron pair qualifies to be the base. Similar example is here. You can have H plus here in solution. And then we have a lone pair of this compound here. That's our ammonia. And it's able to form the ammonium that we are having here. And you can see that once it is accepting, becomes our acid. And this being the base is the one donating, as simple as that. Yes, base, this is where my attention will mostly be. We are talking about pH changes during acid alkali titration. And so when we say acid alkali titration, it can either be the base against the acid or the acid against the base. So the first one we look at is titration of strong base against strong acid. And before we move on, let me mention that whenever you hear anything like strong base against strong acid, the compound or the solution after the word against is the one in your conical flask, or simply put, is the analytes. And the one before the word against is the one in the burette, or is the titrant. Is that okay? Sure. Good. So this time we are looking at an example, a simple example here. We are titrating 1 out of 10 normal sodium hydroxide against 25 mils of 1 out of 10 normal HCl. And then we have been asked to find the pH before titration, the pH after addition of 5 mils of the base, pH after addition of 25 mils of the base, and also the pH after addition of 26 mils of the base. Let's try and understand this better. So we can say that it is basically okay. So we can say, let me take a different color. Okay. So we can say that the whole thing is titrating N out of 10 NaOH against N out of 10 H2SO4. Titrating that against, let me check whether we are on track. Whether HCl. Good. Whether HCl. Excellent. So whether HCl, whether HCl. So we are titrating N out of 10 NaOH against N out of 10 HCl. Good. Like I mentioned earlier, the one after the against is the one in your conical flask, and the one before the against is the one in the burette. That's very fine. Okay. And we have been asked to find one. We have been asked to find one, I, the pH before titration. I have been asked to find the pH after addition of 5 mils. We have been asked to find the pH also after addition of 25 mils. The pH after addition of 26 mils. Okay. Let's see how we go about this. Okay. The first thing to do is, like I said, we have to be able to figure out what is in your conical flask. And so what is in the conical flask is the one that is giving you the pH before titration, because it is the one that you already have before you are titrating the base into it. So when you ask to find the pH before titration, it's basically the pH of what is in the conical flask. So the first one you do is to find the pH of what is in the conical flask by knowing its concentration. The concentration of it, of the HCl that we know, was 0.1 normal. 1 out of 10 normal is same as 0.1 normal. That is the concentration of it. And let me mention that whenever you are solving a calculation and then you hear normality, to get the H plus concentration, don't stress yourself. It is basically the number of normals there. So for example, this one we have 0.1 normal. It tells us that the number of hydrogen ions inside there, is basically 0.1 gram ions per liter. So for normality, any value you have there, so if it is 1,000 normal, it means you still have a population of 1,000 H plus in there. Does that make sense? Good. So this time around, we have 0.1 normal. It tells us that the H plus concentration there is 0.1 gram ions per liter. And so once I know my H plus concentration here, I can go straight to find my pH. We look at a couple of formulas in the previous slide that when I have a strong solution of an acid, a solution of a strong acid, the pH is simply negative log of the H plus concentration. So in this case, our H plus concentration is 0.1. And so by punching this, we are going to get a value of 2 to be our pH. So this is the pH before titration. This is basically the pH before titration. I hope we all understood this. Moving on, let's look at the pH after addition of 5 mils. pH after addition of 5 mils of the base. pH after addition of 5 mils of the base. Good. Now, for addition of 5 mils of the base, we know that once you're adding your base to the acid, the pH is going to be changing, as well as the volume of the solution is going to be changing. Does that make sense? Your pH will be changing, and your base, the solution in the conical flask too, the volume will be changing. That is what you're supposed to take note of. So what you are going to do is that you have to know that the ratio between the various normalities of the acid and the base is 1:1, because it's 0.1 normal of NaOH going to 0.1 normal of HCl. And so the ratio there is basically 1:1. Is that okay? And what this means is that every 1 ml of the base is going to neutralize 1 ml correspondent of the acid. That is what you're supposed to deduce from it. That 1 ml of the base neutralize 1 ml of the acid. And so I can say that means basically we are adding 5 ml of the base. And so by proportion, it will neutralize 5 ml of our acid. Does that make sense? Once you're adding 5 ml of the base, you're going to neutralize 5 ml of the acid. And so if you're neutralizing 5 ml of the acid, we need to ask ourselves, what is then going to be in excess? The acid that was there initially was 25 ml. And we have been able to neutralize 5 ml of that acid. That means our acid will still be in excess. So let's try and find our excess amount of acid. That's going to be 25 ml minus our 5 ml. And that is going to give us 20 ml of the acid. You're going to have 20 ml of the acid being in excess. But I said earlier that our volume of the solution inside the conical flask is going to change, because initially it was 25 ml. And we're adding another thing to it. So the volume, we don't expect the volume to remain the same. So once the volume is changing, we must also work our pH according to the new volume that we are having in the conical flask now. So we are going to find the new volume of the solution in the conical flask. And that was simply 25 ml of our acid that was there, plus the 5 ml of the base that is coming in. And we are going to have 30 ml. Again, once the volume has changed, our concentration will change. So we need to find our new concentration of the solution. And that's basically whatever is in excess. So when you get to this point, you take the volume of whatever solution is in excess. This time around, whatever is in excess is our 20 ml acid. We divide it by the total volume of the solution, that is 30 ml. And you multiply it by the initial concentration of whatever solution that is in excess. I repeat, you take the volume of the solution in excess, or the excess volume of the solution, dividing by the total volume of what you have in the conical flask now, and multiply it by the initial concentration of whatever solution that is in excess. And this time around, it is our HCl that is in excess. So we multiply it by its concentration, which is 0.1. 0.1 normal. And when we punch this on our calculator, we are having 20 divided by 30 multiplied by 0.1. We are going to get 0.0667 normal as a new concentration of the solution. But that notwithstanding, I said earlier that whenever you have anything, any solution with the concentration being in normality, the amount of normality there is the same as the H plus concentration. So I can say basically that this our new solution has a population, or the H plus concentration, the solution there is 0.0667 gram ions per liter. And once I have this, I can go ahead and find my pH. my pH will basically be equal to negative log of 0.0667. And when I point down my calculator, the negative log of 0.0667, I'm going to get 1.17 as my pH. So that is what we have as our pH after addition of 5 moles. Let's move ahead and look at what we are going to have after addition of, so we have done addition of 5 moles. Let's go to the addition of 25 mils. After addition of 25 mils. Okay, so we are going to, after addition of 25 mils of the base. Similarly, you do the same thing here. Okay. Now, after addition of 25 mils of the base, we said earlier that the ratio between them is 1:1. And so therefore 1 mil of the base will always neutralize 1 mil of the acid. What this means is that you're adding 25 mils of the base now. So what do you think will happen? 25 mils of the base. So what do you think will happen? You're going to finish up the acid because it will take care of the same 25 mils of the acid. It means that this thing is simply asking you to find the pH at the equivalence point. When we talk about equivalence point, it's the point at which an amount of the base has neutralized completely the acid that you have in the solution there. So at this point, we have been asked to find the pH after addition of 25 mils. And when you go through the long procedure, you come back to a pH of 7 because all the acid there has been neutralized by all the base. And so you have a pH of 7. So all I'll say is that when they ask to find the pH at equivalence points, simply write the pH at the equivalence point is equal to 7 because when you go through the long process and you come down, you get a pH of 7. So that is what we have for the pH after addition of 25 mils. Let's look at after addition of 26 mils. That's I. After addition of 26 mils of the base. Once again, our ratio is 1:1. So 1 mil of the base will always neutralize 1 mil of our acid. At this time, we are adding 26 mils of our base. So what will happen? We are supposed to have 26 mils of the acid to also neutralize this base, but we don't have. What we have is 25 mils of the acid in the conical flask. It means that this base will finish up the acid and there will be an excess of the base. So what we have to do is that we have to find the excess of the base that is left. But we can only find this by knowing the difference between the acid that was neutralized and then the base that was coming in. So I can say our excess base will simply be equal to 26 mils, that's of the base, minus 25 mils of the acid that was already in the conical flask. And we are going to have 1 mil of the base being in excess. And similarly, I said to find, once we have something being in excess, the volume of the solution will change. So let's now know our new volume of the solution. That's going to be 26 mils of that of the base plus 25 mils of the acid that was already there. And this will give us 51 mils, meaning that our new solution has a volume of 51 mils. And so we have to find our new concentration. Once our volume has changed and something being in excess, we have to find our new concentration of the solution. And that is simply going to be whatever we have in excess. We have 1 mil of the base in excess. and we divide that by the total volume of the solution, that's 51 mils, and we multiply it by whatever solution that is in excess. This time around, it is our base that is in excess. And what is the concentration of the base that we have initially? It was 0.1 normal. And by doing this, when we put this on our calculator, 1 divided by 51 by 0.1, we are going to get 1.96 multiplied by 10 raised to the power negative 3 normal as our new concentration of the solution. But I said earlier that this value here is simply the same as the number of H plus concentration that this time around OH minus concentration that we have. Take note of that. This time around, it is our base that is in excess. So it is no more H plus that we have in the solution in excess, but we have OH minus in excess. So this value here is the same as our OH minus that is in solution. So our conc of the OH minus is now 1.96 times 10 to the power negative 3 gram ions per liter. But then once we have this, we can use this to find our POH. So our POH is now equal to negative log of 1.96 by 10 to the power negative 3. And by punching that on our calculator, we have negative log of 1.96 multiplied by negative 10 power negative 3. We are going to get 2.71 as our POH. 2.71 as our POH. And once we have our POH, we can find pH because we know that pH is equal to 14 minus our POH. And so this is simply 14 minus 2.71. And that is 14 minus 2.71 is going to give us 11.29 or 11.3. That is what we have as our pH after addition of 26 mils. I hope that is very clear. Okay, so let's go back to our slide and look at what we have. Okay, so we can see from here that when we calculated for the pH before the titration, we had 1, and that was exactly what we also had. And then in that same for here, we had 1.17. That's what we also had. And then the pH after addition of 26 moles, we had 11.29, and that is what we also have here. So that is basically how you go about it. Now, there is a solution that we have in terms of normality. This is a solution that you have in terms of normality. Let's try and calculate this in terms of moles, molarity. So in terms of molarity, let's try and see how we can also go about this one. In terms of molarity, let's see how we can go about this one. In terms of moles, this is what we have. Okay, so this time I'm calculating in terms of moles. In terms of moles. Okay. So in terms of moles, in case of moles, we are going to deal with everything in moles. It means that any single thing you do, you must find the moles at that particular point. Or in other words, every single drop of the base that you give out, you must find the number of moles of the NaOH that is inside that drop. Does that make sense? So once again, the thing we are dealing with here will now be 0.01, sorry, will now be 0.1, not 0.01. Now be 0.1 molar NaOH, and then 0.1 molar HCl. That is what we have now. 0.1 molar NaOH and then 0.1 molar HCl. Great. Once we have this, let's try and then find the moles that are already here. The moles that are already here. But we know that the HCl that was there was 25 moles. Right? So our concentration of the HCl was 25 moles, was 0.1 molar. And then our volume of the HCl that was there was 25 moles, which is the same as 0.025 liters. So based on this, I know that I can find my mole of the HCl by saying it's the same as concentration times volume, where my volume is in liters. So my mole now is equal to 0.1 by 0.025. And that is going to give me 0.0025 moles of my HCl. It means that the 25 moles of the acid that was there, there are actually 0.025 moles of the HCl that is in there. Let's do same for the 5 moles of the NaOH that is coming into the solution. But this time around, our concentration of the NaOH will now be equal to the same 0.1 molar, but the volume that we have coming into the acid is 5 moles. And 5 moles is the same as 0.005 mole. 0.05 liters. Does that make sense? This is the 5 moles being converted to liters. So based on this, we can also find our moles of the NaOH that is in the 5 moles by saying it is the same as the concentration by the volume, but the volume has been liters like we've done. We have 0.1 multiplied by 0.005. We are going to get 0.0005 moles. It means the 5 mole that is coming contains 0.0005 moles of our NaOH. Now, we should also take note that the concentrations are 0.1 and then 0.1 for each of the solutions. Therefore, the mole ratio between them is 1:m. The ratio between them is 1:1. Does that make sense? It also tells me that every 1 mole of the base that I drop will take care of 1 mole of my acid. Every 1 mole of the base that I drop will take care of 1 mole of my acid. Great. So it means that once I've added 5 drops or 5 mils of my base to the acid, it will take care of an equivalent amount of the moles of the acid. And so I have to find the excess amount of the acid, excess moles of the acid that is now left in solution. And by so doing, I can say that my excess moles of the acid will now be equal to the moles that is in the 25 moles, that is 0.0025 moles minus 0.0005 moles from the base. When I point this on my calculator, 0.0025 minus 0.0005 5 moles, I'm going to get 0.002 moles of the acid being in excess. Does that make sense? Once again, take note that once you are adding something else to the acid, the volume of the solution in the conical flask will change. And so what you have to do is to find the new moles or the new concentration of your solution. But you can only do that by knowing the new volume of your solution now. And that is simply going to be 25 mils of what was already there, plus the 5 mils of what is coming in. That's going to give us 30 mils. And 30 mils into liters is the same as 0.03 liters. 0.03 liters. Yeah, 0.03 liters. So once we have our new concentration, our new volume now, we can find our new concentration. We know that concentration is giving us mole out of volume, where the volume is in what? Liters. So our moles that we have in excess is 0.002 moles. Then we divide it by our new volume now, 0.03. And this is going to give us 0.002 divided by 0.03. We are going to get 0.0667 molar as our new concentration. So this is a new concentration of our solution. This is a new concentration of our solution. Then I would like to mention that whenever you are working in moles, before you find your pH, you must be able to determine the concentration of the H plus inside that solution. Don't assume, like the normality, that the amount of normals there is the same as the H plus concentration or the OH minus concentration there. No. This time around, you need to determine the H plus concentration of the solution. And how do we do that? You always try to write out the equation of the dissociation of the acid or the base. This time around is the acid that is in excess. So we have our HCl breaking down to H plus, then Cl minus. But initially, the excess that we're having in solution, let's check. The excess that we're having in solution from here, this is the concentration of it, 0.0667. It means that initially we're having 0.0667 moles of the acid. And once it's breaking down, you're going to have the same thing here, 0.0667, and here to 0.0667. But our attention is on the H plus concentration. And so we can boldly say that our H plus concentration is now equal to 0.0667 molar. And once we have our H plus concentration, we can find our pH by taking the negative log of this because it is a strong acid. And so therefore, taking negative log of 0.0667, we are going to have 1.17 as our pH. So this is the calculation for after addition of 5 mils. Let's look at after addition of 25 mils, which is the same, like I told you, the same as the equivalence point. The equivalence point. Okay, the same as the equivalence point. And I said that at the equivalence point, your pH will always be equal to 7. So this is what you need to write, that for equivalence point, your pH is equal to 7. So let's shift our attention to when we add 26 mils. So when we add, so I, after addition of 26 mils of the base, like we did earlier, we still need to find the amount of moles that is in this 26 moles of the base. So our concentration we had was 0.1 molar. And the volume we are having now is no more 5 mils, but it is now 26 mils. And the 26 mils is the same as 0.026 liters. I'm always careful with this because you should know that 0 is the most powerful number in mathematics. So once you make a mistake with your conversation, your conversion, you are going to have a wrong answer. So please, you should be careful about this. All right. So this is what you are going to have in liters. This is what you are going to have in liters. Good. So by so doing, we can find our concentration. Once we have our volume and then our concentration, we can find our moles. Sorry. So our concentration is 0.1 times 0.026. And this is going to give us 0.0026 moles. It means our 26 moles contains 0.0026 moles of our NaOH in the solution. But we found out earlier that the moles of the HCl that was in the 25 mils was 0.0025. Let's cross check. 0.02025 exactly. So 0.0025. That was the mole that we had for the HCl that was in 25 mils. But this time around, we are adding 26 mils of the base. So you can see that the mole of the base here is more than the mole of the acid here. It means that the acid, once the ratio is 1:1, the acid will be finished up and the base will be in excess. So this time around, we find our excess mole of base, no more the acid. Excess mole of the base is going to give us 0.0026 moles minus 0.0025. Does that make sense? 0.0026 moles minus 0.0025. And that is going to give us 1/10 to the power -4 or 0.0001 moles. So this is what we have in excess. 0.0001 mole. It's what we have in excess. Is that okay? Now let's see what happens. Once you have this in excess, once again, your volume will change. So your new volume is now 26 mils of the base plus 25 mils of the acid that was already there. This will give us 51 mils. And 51 mil is the same as 0.051 liters. And once we have this, we can base on this to find our new concentration of the solution. So our new concentration of the solution will now be equal to, as usual, mole out of volume. Now mole here is this, the excess. So 0.0001 divided by 0.051 liters. And this is going to give us 0.0001 divided by 0.051. We are going to get 1.96 times 10 exponents -3 molar. This is what you are going to have as a new concentration of the solution. But take note, I told you earlier that whenever you have this and you want to find the pH, don't just assume that it's the same as what is in the solution, but rather write out the dissociation of your whatever is in excess. This time around is the base that is in excess. So it will break down to Na plus, then OH minus. The concavite that we have is 1.9 times 10 exponent -3. And the same thing happened here, 1.9 times 10 exponent -3. And here 1.96 times 10 exponent -3. But our focus is once again on the OH minus concentration. But once we have OH minus concentration, Bear in mind, we can't go straight and find pH. Rather, we find pOH first by taking negative log of 1.96 by 10 exponent negative 3. Because it's a strong base, we use this formula to find the pOH. So negative log of 1.96 times 10 power negative 3 is going to give us 2.71. And once we have our pOH, we can find our pH to be equal to 14 minus pOH. That is simply 14 minus 2.71. That's going to give us our 11.29, as you can see. So now we are going to figure out something. When we did our calculations in normality, if you remember, the normality that we did, we got the same values. What this means is that when you do your calculation in normality and you do the same calculation in molarity and you get different answers, then there's a mistake somewhere. So whether you use normality or molarity, you must arrive at the same answer. So this is the solution of what we have. Okay, let's move ahead. So we can see that he did similarly here, and he got the pH for 1.17, like we did for after addition of the 5 mils, we got this. After addition of 26 mils, we got the same thing that we had here. Is that okay? So whether you solve in moles or you solve in normality, you should get the same answer. Now let's look at what happened to the graph. What happened to the curve? Okay. What happened to the curve when you have an acid-base titration? So this is a titration of, you can see from here, strong base against strong acid. Strong base against strong acid. So once strong base against strong acid, it means the base is the one that is originally, the acid is the one that is originally in the flask. Then the base was being added to the acid. So once it is a strong acid, we don't expect the pH to be very high. So you can see from here that the pH on the pH axis, the pH is starting from somewhere here, because we found the pH to be 1, as you can see. Found the pH to be 1 here. And so it's starting from somewhere here. Somewhere here. Does that make sense? Now, this acid will be there at the same pH until you start adding your base, the pH won't change. After you start adding your base, what happens? You realize that the acid will be neutralized. The acid will be neutralized. And the base will start taking over. And once you're neutralizing the acid, once you're adding base, you'll be increasing the pH of the acid. And so you realize that the curve will be rising. The curve will be rising. So the curve was rising, as you can see. The pH was increasing. After addition of when you're adding your base, the pH will be increasing until a point where the acid is finished and we are left with only the base, the solution. Then the curve becomes flattened or becomes constant, because at this point acid was there and we are finishing up the acid. So the curve will be rising, the pH will be rising, increasing until the acid is finished. Then you're left with the base. So the horizontal one represents the pH of the base that is now in excess. Does that make sense? Good. Similarly, if you have a titration of a base, a strong base against a weak acid, the same thing will happen here. Remember, we are saying the one after the gains is the one in the conical flux. It means your weak acid was the one in the conical flux. So you can see that the pH didn't start from somewhere very low as the first one. It's from somewhere high like this. And once you start adding your base, automatically your curve will start rising. The curve started rising because the pH will be increasing. Is that okay? It will be increasing until a point where the whole of the acid has been finished and then it becomes flattened. Similar as the previous one. All right. Now we are looking at a few principles in hydrogen ion concentration. We are saying that whenever you titrate, whenever you mix a solution of a strong base and a weak acid, they are going to form an alkaline solution. Whenever you mix a strong base and a weak acid, you form an alkaline solution. And why is that so? That is what we want to look at. Now, you realize whenever you mix a strong base and then a weak acid, there'll be a salt formed. So, for example, when we mix acetic acid and NaOH, we are going to form sodium acetate as our salt. And this salt, the salt of a weak acid is always strong, and the salt of a weak base is always strong. So this salt, once it is strong, it's going to break down easily in solution. So here we are representing acetic acid, the whole of this, by AC. So when you see AC, it's acetic acid. So this is the salt that has been formed in the solution. And it being a strong salt, it will break down easily into its ions. So you're going to get the sodium ion and the acetate ion, anion, inside the solution. And once this salt is in a medium of water, remember, water will break down into the OH minus and the H plus. And so there will be interaction between these ions in the solution. There will be interaction between these ions in the solution. Is that okay? And what are you going to see? You're going to see that there will be interaction between the sodium ion and then the hydroxyl anion in the solution. So negative and positive will go together. The sodium ion will form a bond with the OH minus. Does that make sense? Form an OH minus. But this thing formed here is also a strong base. So by so doing, it will still break down. To still break down in what? Solution. To still break down in solution. Na plus plus OH minus. To still break down in solution. Does that make sense? Good. Once it is still breaking down in solution, meaning the OH minus will still be in solution. But for a reaction between the acetate anion and the H plus, it's going to give us acetic acid, which is a weak acid. So its dissociation is very poor. So it's not going to be breaking down as how the NaOH will be breaking down. Does that make sense? It means that we are going to be deficient of H plus in the solution, meaning the H pluses of the water will be mopped up by the acetate anion. So overall, what is happening is just mopping up of H plus ions in the solution and abundance of OH minus in the solution. And so we are going to have our solution ending up to be alkaline. Does that make sense? So this is based on the same idea that I used to explain what will happen if you have a strong acid and a weak base, similar to what happened. So they're based on the same idea. You can explain. Okay, so let's come here to the same thing will happen here. We're having a reaction between a weak, we're having a reaction between this, a reaction that has produced, I have a reaction that has produced this salt, NH4Cl salt. Okay. And I said earlier that this is from, you can see it's from a strong acid, HCl, and then a weak base. Okay. This is what we have. We are producing this salt. Once we have the salt of a weak base, it's going to be strong. And so we'll break down in solution into this. Water will break down, and there will be interaction between the ions. We are going to form HCl here, which will easily break down. So HCl is a strong acid, will break down to H plus and then Cl minus. But this is going to give us a weak base, which will not break down as how the HCl will break down. It means we are going to be deficient of the OH minus. This OH minus will mop up in solution, and there'll be abundance of H plus in the solution. And so our solution is going to turn out to be acidic. Okay. Let's base our attention right now on buffer solution. buffer solution. Buffer solution. Buffer solution is simply any solution that is able to resist change in pH upon addition of small amounts of acid or base. Please, this word is very, very, very important. Small amounts of acid or base. So when you add a small amount of acid to the buffer, it must be able to resist change in pH. When you add small amounts of base to the buffer too, it must be able to resist change in pH. Now, how do we form a buffer? Buffer is formed simply between one, a weak acid and any of its salts, or a weak base and any of its salts. Whenever you combine a weak acid and any of its salts, you're able to get a buffer solution. When you combine a weak base and its salts, you're going to get a buffer solution. So we can have acidic buffer solution or acid buffer and then a base buffer. Does that make sense? So a typical example is here. This is a buffer of acetic acid and then sodium acetate. Sorry, sodium acetate. This is a weak acid and this is a salt, a strong salt. And so this qualifies to be a buffer. We are good to go. Great. Now, what happens if the buffer is there and then you add an acid or a base? You can say that the acetic acid was able to break down to H plus and then acetate anion. And then the salt was able to break down to give us Na plus and then acetate anion. So let's assume that we are adding an acid, which is H plus, to the solution. This H plus can go and bond with the H plus. It can also go and bond with the Na minus, but it will come and form a bond with the acetate anion in the solution, producing more of the acetic acid. So basically, you're just reversing the reaction. It means that once you add that H plus, the buffer will try each possible way means to neutralize it and bring it back to its original position. But when you add a base, what will happen? For addition of a base, this base cannot go and react with the acetate anion. It can also go and react with this, but rather to come and react with the H plus to give us to be mopped up by the H plus. So we can see that from the statement, we are saying excess acetate ions will react with H plus ions, which might be added like this. And then the excess acetic acid will react with the base to give us to stabilize the system. Does that make sense? Good. Now we have a scientist, two scientists actually. We have Henderson and then Hessel. And then we are saying that they came up with an equation of a buffer. That's what we call the Henderson-Hasselbalch equation. And I'll urge you to know how to prove this. I'll urge you to know how to prove this. So let's try and prove this. This is the Henderson-Hasselbalch equation. Here is it. And this one is for an acid buffer, meaning we can have one for the basic buffer too. So let's try and make something out and see how best we can understand this. All right. Okay. So let's start. We are saying that if you have a weak acid, okay, if you have a weak acid, a minute. So if you have a weak acid, which is basically acetic acid, our most popular example that we can use here. Let me represent this by just HAC. And when you have this acetic acid is a weak acid. So we'll be able to dissociate partially into solution to give us H plus and then the acetate anion. This is what you're going to have. But from basic chemistry, you know that to find the Ka of this is going to be the product of the concentrations of the product of this dissociation divided by the concentration of the acetic acid or the reactant. This is what you have for Ka. But our attention is to find the pH of the solution. It means we have to make H plus the subject. So by making H plus the subject, I can just multiply it through by the conc of this and multiply here too by same thing. So this can take care of this. So I'm going to have this as my fallout, Ka, giving me H plus multiplied by the conc of AC minus. But my attention is here, so I'll still divide through by this. I'm going to get my H plus to be this. Let me just write it this way. I'm going to have this divided by the acetate anion. This is what I will have. But once I want to find pH, what do? I take the negative logarithm. Okay, I take the negative logarithm of both sides. So I'll take negative log of H plus. Now I'll take negative log of this side too. Take a negative log of this side too. That's what I have. By basic logarithm once again, this, or I can split this thing. Watch here. I can split this to be this. I can have this. I can have this. So it means that I can simply write this. The whole of this side is pH. I can write this as pH being equal to negative log by basic logarithm principle, negative log of Ka plus, once it is negative log that is coming there, I can just replace the whole of this by minus. So minus the log of this over that. Simple as that. This is what I have. But we know that negative log of Ka is same as pKa, right? And because we don't normally like to work with negatives, we try to be at the positive hand side. So I can translate this by saying that I'll turn this into plus. And once I turn this into plus, I have to reverse this side. So I have plus log of, then my acetate anion now comes to the top, and acetic acid is now at the down. So this is what I have for the Henderson-Hasselbalch equation. It is not bad if you write it this way. It's not bad at all, but you have to be extra careful when you're doing your manipulation. We can also have this. Somebody can choose this and choose this. But mostly we prefer to use this because we don't normally want to work with negatives. Good. So this is the Henderson-Hasselbalch equation for a weak acid. For a weak acid. So I can translate the whole of this by saying that pH is equal to pKa plus the log of. Now, when you look at this, this is the conjugate base of the acid from the reaction that we did here. This is a conjugate base of it because they are different. The difference is hydrogen. This conjugate base is simply what to go and form the salt. So I can say that this is the same as the log of the concentration of the salt over the concentration of the acid. So this is where our final decision lies. As our pH is given as pKa plus the log of the conc of the salt divided by the conc of the acid. This is for weak acid. Let's look at a basic buffer and look at how we prove that one too. For a basic buffer, okay, for a basic buffer, let me use a common example. Okay, let me use this and then this. Okay, so this is what we have. This is what we have, right? So if I have a base, let me use this to represent a base. If I have a base, BOH, this base, this big base is going to break down. It's going to break down to give me this and then that, OH minus. Similarly, I can find my KB from here by saying my KB is just the product of these two. Divided by this. Exactly. But my attention is on the OH minus concentration. So I'll try and make this OH minus concentration the subject. I'll try and make this the subject. So I'm going to have my KB multiplied by BOH, which is going to give me my this multiplied by OH minus. But to find the OH minus, I still have to do some work. So I'll divide through by B plus. I'm going to get KB multiplied by BOH, or divided by B plus. All right, so this is what I'm going to have. OH minus giving me B plus. OH minus conc giving me KB multiplied by BOH divided by B plus. This is what I have. Okay, good. This is what I'm going to have. Now, let's work something out here. Let's work something out here. From here, okay, from here, we can find our POH. So my POH is simply going to be the negative log of OH minus. And once I do this, I do same for the other side too. I'll take negative log of my KB multiplied by BOH all out of this. This is what I have. So this side becomes my POH. This is going to give me, like we saw earlier, this will be negative log of KB. Then I'm going to have minus the log of BOH concentration out of the conc of B plus. This is what I'm going to have. So my POH furthermore will be equal to negative log of KB is the same as PKB. Is that okay? It's the same as PKB. And this is going to give me minus log of BOH all out of B plus concentration. Right. But we want to find pH. We want to find pH. Okay, we want to find pH. It means that we have to find a way of converting this pH, POH into pH. But we know that 14 is equal to pH plus POH, or in other words, what we call pKW. pKW, that's the ionic product of water. Okay, it's the same as pH plus POH. So I can replace the whole of this. That means my POH will be equal to pKW minus pH from here, minus pH. So I can just translate here into pKW minus pH. This will give me my pKb, then minus log of what I have here, BOH, out of the concord B plus. Right. Once I have this, my attention once again is to make pH the subject. So I'm going to have negative pH, giving me pKb minus pKw minus log of the whole of this, BOH, out of B plus concentration. This is what I'm going to have. But I want to get rid of my negatives. So I'll divide each and every part by negative. Or better still, I'll multiply each and every part by what? Minus 1. So I'm going to get pH being equal to negative pKb plus pKw, and then plus the log of this, BOH, out of B plus, out of B plus. Good. And once I have this, I can further rearrange, okay? I can further rearrange by saying that my pH is now equal to my pKw minus my pKb plus the log of my base out of its conjugate over there. So there's what I have. So once I have this, I can still write this as pKw minus pKb plus log of, and I'll write this as my conc of base out of my conc of the salt. This is what I have for the hardness. So Hazelbach equation for a base buffer. This is what I have. So in summary, we are saying that for an acid buffer, our pH is equal to pKa plus the log of the conc of the salt divided by the conc of the acid. And for a base buffer, our pH will now be equal to pKw, or better still, we can write 14, okay, 14, minus pKb, okay, plus the log of, this time around, it turns around, becomes base out of the salt. So these are the two equations that you have to have at the back of your mind for calculating the pH of a buffer solution. So coming back to the slide, we saw this, now we can understand where this is coming from. And then also, we can understand where we can also prove where this one is coming from. The pH of the basic one is coming from. Right, so now when we say this, we can now be able to prove. So please know how to prove this, and then we are good to go. Now, once we have this formula, it tells us that we can find the pH of anything at all, any buffer solution at all. So for example, there's a question here, a buffer solution containing 0.1 molar acetic acid and 0.1 molar sodium acetate will have a pH of 4.7. So let's try and find it out. We are saying that the buffer has a pH, the buffer has a concentration, okay? It contains acetic acid. It contains this, the concentration of acetic acid in it was 0.1 molar. Then the concentration of its salt, okay, is 0.1 molar. The first question you should ask ourselves is that, is this an acidic buffer or this is a base buffer? And from what we have here, it's an acid buffer. So the next thing to ask ourselves is that which formula are we going to use? We have to use the formula for the acid buffer. So simply put, our pH will now be equal to, how do we get our pKa? We get our pKa by taking negative log of our Ka. So our pH will be equal to negative log of 1.8, which is our Ka, times 10 power negative 5. Then plus the log of the conc of our salt, which is 0.1, divided by the conc of our acid, 0.1. And by punching the whole of this side will give us 1. The log of 1 is always 0. We're going to get 4.74 as the pH of the solution. So any buffer you are given, just be able to tell yourself or ask yourself, is this an acid buffer or a base buffer? And then know the formula you're supposed to use, and then you are good to go. Is that okay? Good. Right. Now, so we've mentioned this earlier. An alkaline bypass solution contains weak base together with its source. We've said this earlier, and this is a typical example. And you should be able to prove this. Now let's have the last example in the slide, which is this one. We said a solution containing 0.1 moles of ephedrine is pKb of 4.64 and 0.1 mole of ephedrine hydrochloride per liter of solution has, so we are supposed to find the pH of this. Now, take note of this, per liter of solution. It means all of these moles are in 1 liter. And so simply, this is the same as the concentration of the various things. So we have ephedrine. Let me use this for ephedrine. And it has a concentration of 0.1 molar. And we also have ephedrine hydrochloride. Okay, 0.01 molar at the concentration. Now the question is to ask ourselves, what type of buffer is this? This is a base buffer because it contains ephedrine, which is basic. Even if you don't know, they have given you pKb there, so that should tell you it's a base. And then its salt is the ephedrine hydrochloride. So by so doing, to find the pH, we can say that our pH, by knowing the formula, will be equal to our 14, like I told you, the pKw is the same as 14, minus our pKb, and plus the log of the conc of the base, which is 0.1, and then divided by the conc of the salt, which is 0.01. Then you're going to get 10.36 as your pH. Be very careful not to interchange them, so you should know what you are doing, and then you are good to go. All right, so that is what we basically have for the buffer, and as well as pH calculations. We shall look at more examples the next time we meet. Thank you again for your attention, and have a wonderful time. Thank you.